Hi, my name is Yannick Zakowski, and today I'll have the pleasure to discuss with you a quite famous intermediate representation that is named Static Single Assignment, or SSA in short. Before delving into technical details about its definition, why it's called like that, let's start at a much higher level to try to motivate what we are trying to do. We are going to start with very high-level considerations that you are quite familiar with, I believe, by now. What is a compiler about? It's essentially a two-folded task. Compiling is about computing some information, some invariants about the program, and more specifically information about program points of the program, which is what we call usually the data flow analysis. And the counterpart is to use this information in order to justify some program transformation, hopefully some optimization on average, that are semantically correct because in this specific case, we know some information about the program we are transforming. And so we see that there is, of course, this duality between the definition side of a variable, where we compute and associate to this definition side some information, and the moment, the physical position where we exploit this information, which is the use side of a variable. For instance, if you consider this very small example on the right-hand side, we could, for instance, infer that at this first program point, x is exactly equal to 3, or at the second program point, y is even. However, it is at this third program point, when we actually are associating x plus y to z, that we are interested in this information. And we wonder, at this point, what do we know about x and y? So this, of course, is a very common and very basic problem of compilation, which means that we essentially need to have a very efficient way to, given a use site of a variable, retrieve its deficient sites. To do so, a common solution is to use data structure, of course, which is usually called the def use or the reciprocal, which is a use def chain, where essentially you carry on a set of pointers that associate to each use point of a variable the set of definition points that are pertinent to this use in the graph. The problem with this data structure is that in the worst case, if your variable has meets m definitions on n uses, then you end up with something that has a quadratic space and time complexity of the product of this n and this m. So the idea behind static single assignment is basically to say, could we make this data structure completely trivial, completely explicit in the syntax of the program? And intuitively, one way to achieve so would be simply to have m equal 1, meaning that each syntactic variable is only defined once. Well, since we want to enforce an invariant by construction on all programs, what we want is an intermediate representation. This intermediate representation is single static assignment. Once again, very simple idea. Each variable must have exactly one definition in the syntax. This means that use def chain will be completely explicit, and we will see that as a consequence, many optimizations are simplified. One important remark, we are saying that there is only one definition point of each syntactic variable, but that means that there is only one dynamic assignment. Indeed, there might be a loop, and we might process this assignment many times, potentially infinitely often. It is not the single assignment intermediate representation that would be basically purely functional programs. This intermediate representation was introduced quite late when we think about how simple the idea seems, at least at the first glance, in 1988, but is now used in most modern compilers. To be a little bit pedantic, note that we have defined here a property to qualify our intermediate representation as SSA. Each variable must have exactly one definition syntax. We are not assuming anything about the data structure that is used to represent the programs themselves. And so more specifically here, as a way to illustrate what we are trying to describe, we will more specifically use control flow graphs in SSA form. All right, let us start therefore with the conversion of a given program into SSA form. And we were going to start informally to try to get some intuition as to how can we transform a program such that each variable has exactly one definition site in the syntax. Let's consider first some straight code, so just a block, here PL on the left-hand side. And as we've discussed, the program is quite obvious. we have here two uses of the same piece of syntax, the same string A, for two distinct definitions. Of course, the solution is quite easy to come up with so far. We'll just introduce indexed versions of our variable by using a fresh version of A at each of its def sites. And we, of course, then need to adapt the right-hand side, the use sites, in accordance. For instance, here with these three uses of A, and here the rule that we will follow is simply to use the most recent definition at each use site. So A1 in the two first cases, but A2 in the second case. Now, if you try to go toward fancier control flow graphs, could wonder whether having disjunction points, so conditional jumps, will bring any new difficulties. So here with, for instance, BI, that jump either into BL or BR. Well, actually it doesn't change much of any difficulties. Maybe just one remark is that, as you see here, we introduce A3, so we need to be slightly careful that the notion of freshness is not local to blocks. It has to be a global notion of freshness. But it's still fine. We still use the most recent definition at each use site. Things get a bit more interesting when we actually consider merging nodes. Consider this time that we have this BF at which both BL and BR are merging, and that it is using the variable A. The problem here is that this time our notion of most recent definition for this A is suddenly ill-defined. It could be either A2 or A3. The idea behind SSA is to introduce a new kind of instruction, a phi node, that will have a quite surprising semantics, at least slightly uncommon semantics, in the sense that its operational behavior will depend on the control flow. More specifically, here you see that we have this new assignments, A4, that receives a phi node that will is parameterized by A2 and A3, so two variables, but also BL and BR, that are two block identifiers. And the idea is that if I have reached this phi node jumping from BL, then I will load A2 into A4. If I have reached it from BR, that is A3 that I will use. Now that we have introduced a fresh new version of A4, we can simply use it in our initial use site. So the whole idea behind converting into SSA form is essentially to figure out when to introduce such phi nodes. And actually, we need to refine, to be a bit more ambitious with ourselves, because of course one solution would be to simply introduce one phi node per variable at every join point. But if we were to do so, we would introduce an absurd amount of spurious variables, which would essentially defeat the purpose of the representation. So more specifically, we want to introduce as few phi nodes as possible.